In the cloud, time equals money. I like this statement. Slow computations indeed cost more, but they also harm environment in terms of energy, heat, waste, and pollution. Today, we explore how green data processing with Python 3.12, Polish library, and ARM-based CPUs can help. I'm Sterkin. I'm a software engineer for many years. If you are interested in more details, feel free to look at my LinkedIn profile. Let's set the stage. Starting with version 3.11, Python performance has improved by 60%, and we expect another 5% improvement in the version 3.12. The Polish library is said to be significantly faster than Pandas, and ARM-based CPUs are advertised as more environment-friendly and more cost-efficient than Intel and AMD-based CPUs. We will test these claims with Python 3.12, Polish library, and AWS ARM-based Graviton CPU family. My primary goal in this presentation is to suggest a methodology and initial architecture for systematic Cloud Python benchmarking. Part 1. AWS. Currently, AWS offers two ARM-based CPUs, Graviton 2 and Graviton 3. Graviton 2 has a wide range of configurations. It supports serverless Lambda, Fargate, virtual machines, and outposts. Fargate and virtual machines could be configured into Kubernetes or regular container clusters. Graviton 3, on the other hand, offers only virtual machines that could be integrated in Kubernetes or plain containers non-Fargate clusters. Graviton 3 is advertised as 25% faster, but it costs more. It's important to keep in mind that this offering might change after this year's annual reInvent conference announcements. Another consideration to keep in mind that fully managed options are usually easier to develop, easier to maintain, easier to operate, but they do not provide enough control over cost and scalability. Non-fully managed configurations provide more control, but they are more expensive to develop, maintain, and operate. In order to evaluate performance, we need to run benchmarks, and for benchmarks, we need computation platforms. AWS offers three primary platforms for computation: virtual machines, containers managed or not, and Lambda functions, each one with its own resource constraints and payment models. While Lambda functions would be probably most cost-efficient option for running these benchmarks, it currently doesn't support Graviton 3, and running standard benchmarks on that platform would require significant adaptations. Therefore, we will run all benchmarks on virtual machines. I'm currently working with the AWS EU West 1 Ireland region, and if I type that command, it will report that there are 670 different instance types in this region. Testing all of them would be impractical and cost prohibitive. After some analysis, I chosen to focus on three instance types: T family, M6 family, and M7 family across three CPU architectures: Intel, AMD, and ARM. The T family features what is termed burstable instances, assuming used in the fully managed environments like Fargate and Lambda. M6 family contains older generation CPUs, including Graviton 3, and M7 family includes a newer generation of CPUs, including Graviton 3. We will run three benchmarks on two Python versions on 9 instance types. Totally 53 data points, which I believe will be statistically significant. To ensure consistency and eliminate any possible distortions caused by lack of resources, all instances will be of size extra large, 4 virtual CPUs and 16 gigabytes RAM. we will use T3A extra large, which is AMD-based burstable instance, as our baseline. I believe this is the closest approximation of fully managed Lambda and Fargate environments. To effectively compare different configurations, we need some metrics based on benchmark results. It's a usual practice to plot metrics on some line with baseline in the middle and winners and losers occupying 5 extremes, and sometimes useful also to plot second best choice. Before we select metrics, it's important to clarify optimization goal, what we're actually trying to achieve. I suggest, in the context of this study, to aim at finding the least expensive configuration that still implements system requirements in terms of latency and throughput. In order to compare our different configurations, we need to calculate metrics. AWS suggests so-called price to performance ratio by dividing performance gain by price reduction. Unfortunately, this metrics is too much performance improvement biased. For example, if we have 50% performance improvement and 30% cost reduction, we will get very impressive 167 score. However, if we have 30% performance improvement with 50% price reduction, we'll get a modest 0.6 score. In the AWS Lambda environment, in both cases, we will get impressive 65% transaction cost reduction, provided the 30% performance improvement is sufficient for SLA. So we need a more balanced metric. After some experimentation, I came up with dual set of metrics. The first one is transaction duration ratio, TDR, which is calculated as a benchmark completion time divided by baseline completion time. It's different from sometimes more often used transaction performance ratio, TPR, when baseline completion time is divided by benchmark completion time. It's a flipped equation. The problem with this metric is that it could create false impression of improvement. For example, 100% TPR, 50% performance improvement, actually means only 33% duration reduction. To get 50% duration cut, we need 100% performance improvement. So this TPR matrix is less suitable for price performance benchmarking. TDR for a complete benchmark will be calculated as a geometric mean of individual benchmark TDRs. To calculate transaction cost reduction metric, we will calculate price ratio as a benchmark instance price divided by baseline instance price, and then we will calculate TCR as 1 minus benchmark TDR multiplied by price ratio, and we will take arithmetic mean average to calculate benchmark set TCR. Transaction duration ratio and transaction cost ratio reduction have different sensitivity to extreme values. TDR is calculated as a geometric mean and it's less sensitive, and TCR is calculated as arithmetic mean and it's more sensitive. When these two metrics diverge, it provides an additional insight in underlying performance versus cost and consistency dynamics. Having these two metrics allows us to plot them on a two-dimensional space with baseline in the middle, winners gravitated to bottom low corner, losers to upper left corner, bottom left for trade-offs when we have higher performance but also high price, and upper right corner when we have cheaper options but slower. And that also allows us to plot a second best choice. While this structure might look unusual, it's very accurate and it works very well in all practical cases. System architecture. Executing three benchmark sets, one for Python, two for Polars, on two Python versions, on 9 instance types, is a complicated task. We need to launch instance, we need to install prerequisites, to install 2 version Pythons, to install all necessary libraries for 2 versions, run benchmarks, collect results, upload them to central storage, terminate instance. Once we finished with all instances, we need to calculate the final scores and upload them to the central storage. Performing all these tasks manually would be slow and error-prone. Therefore, I decided to automate the process at reasonable level, and I'm going to share with you the highlights of the system cloud architecture. The first point is that we need central storage. For that purpose, we will use Amazon S3 blob storage. The second is we somehow need to connect to instances. Using SSH traditional technique is an overkill and cumbersome in this environment because instances are short-living. Amazon Session Manager provides a very convenient way to connect to instances in order to launch scripts, installation, and benchmarking without exposing instance to internet. To achieve that, we need to define instance profile and virtual private cloud security group that will isolate instance from internet. All these common resources are grouped in AWS CloudFormation stack. Individual instances also launched as a separate CloudFormation stack. We will use spot instances to save cost. All sources are kept in GitHub Git repository, and the whole process could be orchestrated from AWS Cloud Shell. This architecture is not perfect, but it worked well for that project. If the system evolves and starts to be more production grade, some significant changes will be required. Part 4 Python. From version 3.10, many important new features were introduced, such as structured pattern matching, improved metaprogramming, improved exception handling, improved parallel programming, and profiling. For version 3.9 up to 3.11, there are official support in there is an official support in Amazon Lambda and official Docker images based on Amazon Linux. For version 3.12, custom Docker images will need to be created, which requires additional development and maintenance effort. We don't need to compare all Python versions because that's well-known fact that 3.11 is significantly better than in performance-wise than previous versions. What we need to compare 3.11 with 3.12 on different instances in order to figure out whether developing custom Docker images is justified or not. How Python itself is built has a very strong impact on the overall performance. According to the PyEnv tool recommendation, there are special flags that, if invoked, they lead to up to 30% performance improvement. Official Docker images use some of these flags, but not all of them, and therefore I decided to postpone Docker images investigation and to run all benchmarks directly on virtual machines using the PyEnv tool. Building fully optimized Python takes about 20-30 minutes versus less than 5 minutes for non-optimized version. Performing that task for every instance would be slow and costly. Therefore, I decided to build it once. We only need two versions because Intel and ARM share the same Python build. Package them as .gz file, upload to central storage, and then every benchmark instance could just download it, unpack put in the right place. That significantly improves the overall instance bootstrapping process. Now we could turn our attention to Python benchmarks. There are many Python benchmarks around, each one trying to check certain features of the language or compare it with different languages. It's very important to use official standard Python benchmark set, which is called PyPerformance. And these are results for all these instance types. The clear winner in T family is T4G, Graviton 2 based, with Python 3.12. It has impressive duration reduction and price reduction. In the M family, the winner is Intel-based M7i, very impressive performance reduction, improvement, and very impressive cost reduction. Graviton 3-based M7G has comparable cost reduction, but it's slower. It's still a valid choice to consider because it's more environment friendly. We could plot these results on the graph. Here is our baseline. This is the winner in T family. This is the winner in M family. This is the next valid choice, second choice. And this is a laggard T3A, the same instance type as for baseline, but upgraded to Python 3.12. Part 5, Polars library. Polars library, like very popular Pandas, belongs to a category of data frame processing frameworks. Data frames are general-purpose two-dimensional data structures with columns and rows, similar to database tables or spreadsheets. Polars was developed in Rust, applying very aggressive multi-threading techniques that led to very significant performance improvements comparative to all other libraries. It provides very convenient Fluent API in Python or SQL, lazy evaluation, very convenient for exploratory data analysis, and mid-size extract, transfer, and load pipelines. All statistic calculations of all scores in this project were calculated using the Polars library. If file size are beyond several hundreds of millions of records, then Polars might be not the best choice, and there is a need to consider distributed data frame environments like Spark. As in the case of Python, it's very important to use official standard benchmark for Polars. Polars decided to use TPCH benchmark suite. TPC stands for Transaction Performance Consortium, supported by many companies. Polars runs benchmarks using 3 different types of sizes of file. Parquet files, scale 1 small, scale 5 medium size, scale 10 large size. For some technical reasons, it was impossible to create a scale 10 file. It requires additional investigation. So let's look at results of scale 1 benchmarking. Again, in T family, T4G, Graviton 2 based instance is the winner, more or less the same data. In M family, Graviton 3 based M7G is the winner. However, AMD based M7A is a close, strong candidate for second choice. It's faster, however, it's more expensive. Here's the graph, baseline, winner in T family, winner in M family, close second candidate, which is faster but slightly more expensive, and this is a loser T3 Intel-based burstable T3 instance with Python 3.12. These are results for scale 5. Again, in T family, T4G, Graviton 2 based instance is the winner, more or less the same numbers. In M family, Graviton 3 M7G again is a winner, with plus minus the same data, and AMD-based M7A is a strong second choice candidate with impressive performance improvements, but more expensive. The results are more or less consistent between two sizes of file. We need to see what will happen with scale 10 sizes. Graph, baseline, T family winner, M family winner, second choice, and the loser. It's time to collect our findings and derive some conclusions. So this table summarizes what we found at the benchmark in benchmarks. In T family, T4G Graviton 2 based instance was a winner across all benchmarks. In M family, for standard Python performance test, M7I was a winner with M7G Graviton 3 based instance as a second choice. For polars, scale 1 and scale 5, consistently Graviton 3 based M7G is a winner, and AMD based M7A is a strong second choice candidate. As I said, it's faster, but it's more expensive. Some final comments. Cloud Python benchmarking at scale requires skills and tools. It's not an easy task. Selected a dual set of TDR and TCL metrics work very well. I'm pretty satisfied. I do not recommend aggregating metrics across different benchmark sets. It could create a lot of distortions here. Results suggest further investigation of T4G for fully managed Lambda and Fargate, and across M family, Graviton 3 based, Intel based, and AMD based in M7 family for non-Fargate regular containers or Kubernetes containers clusters. Unfortunately, different benchmarks use different timing mechanism, and that invites some standardization effort maybe in the future. PyPerformance benchmark concerned me because it combines standard Python features benchmarking with third-party libraries that might create some confusions here. And the last advice, make your cloud architects to pay for resources. Believe me, it makes huge difference in the decision-making process. That's it. Here are my social contacts. Reach me out if you have any questions or comments. And thank you for your time and your attention.